And make sure you can see Robert. Can you see Robert? Maybe we'll move this. Okay, so I will stay 2 meters away from everyone. So I'll remove my mask just for the introduction. So welcome everyone to this edition of the Physical Society Colloquium in person for the first time in about 18 months. It's a pleasure to have everyone here. And you may have noticed, if you looked at the colloquium schedule, that for the first 2 months of the academic year, we have speakers coming to us from the Montreal area. This is due to travel restrictions and funding travel restrictions. But it's not unprecedented. In fact, it used to be that at McGill in the physics department, we had local speakers regularly. And even I looked back at old issues of the McGill Reporter, and you can go back to the October 2009 edition of the McGill Reporter. There's a quotation from a former McGill professor there about a physical society discussion. And this professor said, "We are having a great discussion tomorrow in our local physical society when we hope to demolish the chemists." Some of you may have guessed that this was the future Nobel laureate in chemistry, or Ernest Rutherford. So it's a great pleasure to introduce one of our esteemed colleagues, Professor Robert Brandenberger from McGill University, of course, who is a member of the Department of Physics and the McGill Space Institute. Robert did his studies at the ETH in Zurich in his native Switzerland, after which he did a PhD at Harvard University. He was a postdoc in the group of Stephen Hawking at the Division of Applied Mathematics and Theoretical Physics in Cambridge. Then a postdoc at the Institute for Theoretical Physics at UCSB, University of California, Santa Barbara.
The other way around.
The other way around? Oh, I'm sorry, you should update your Wikipedia page. He then went to be a faculty member at Brown University and came to McGill in about 2004 as a Canada Research Chair Tier 1, and is currently a Canada Research Chair in Theoretical Cosmology. He has a number of awards, including a Sloan Fellowship, the Outstanding Researcher Award from the Division of Energy, the CAP CRM Prize in Theoretical Mathematical Physics, and he is a Fellow of the American Physical Society. So please welcome Professor Robert Brandenberger.
So thank you very much for the introduction, and thank you for the invitation to give this colloquium. It's a great honor to be able to give this colloquium, and it's wonderful to see all of you. In fact, I'm here seeing a couple of people in person for the first time. Now, I need to do a sound check. Do those of you in the back hear me if I speak like this? Yes. Okay, wonderful. Good. So, this is my program today. I will first try to convince you that cosmology is an exciting field. So this is only the introduction. Now, since I think it's a rather exciting field, the introduction is going to be rather long. So now, after this rather long introduction, I will turn to our current paradigm of early universe cosmology, which is the inflationary universe scenario. This was developed in the 1980s, and it's been with us since then. And, well, it's been with us since then. It has not made so much progress. And you see, at this point in the colloquium, there will be a transition from things which are accepted generally in the community to things which are not generally accepted in the community. And I will remind you when I get to this point that you should then start being a bit skeptical about what I'm saying. Okay, now there's a Vicky Weisskopf, who was a professor MIT for a long time, he had a recipe for a talk which says that one should start with something which everyone explains, everyone understands, and one should end with something which not even the speaker completely understands. And I will try to follow this. So when I get to this part here, I will try to indicate some new ideas which we are playing with, which are not completely worked out. I think they are promising. I'm trying to persuade you that they are promising, but they are not completely worked out. So here, I will try to deconstruct inflation. I will try to convince you that this current scenario of early universe cosmology, well, you might be a little bit skeptical. There might be alternatives. There are alternatives, and the alternatives might be better. So this is the menu for today. So cosmology is an interesting field because there are some very basic questions that we would like to address. What is the origin and early evolution of the universe? Now these are questions which humanity has been asking for centuries, in fact for millennia. Now what's made cosmology into a science is that we have instruments and we have data. Now cosmologists are very lucky because the instruments that cosmologists use, now cosmologists who do observations, not like myself who's a theorist, we don't get to go to these nice places. But anyway, these instruments which cosmologists use are not in a basement without windows, but they are beautiful spots on the surface of the Earth, for example, the Chilean Andes. So this is an optical telescope. And with these optical telescopes, we look at the sky, and we see these beautiful structures, these galaxies. Now for a pencil and paper theorist, these are much too complicated. So we will replace this beautiful galaxy by a point, and we will probe deeper. And we will make a map of the distribution of galaxies over the entire sky. So this is a projection of the sky onto a plane, like the projection of the surface of the Earth onto a plane. And each point stands for galaxy. And the only thing I want you to take away from this is that there are regions in the sky where there are more galaxies than average, and regions, for example here, where there are less. So there is structure. Now, optical telescopes, that's not the only way to probe the universe. There's also microwave radiation which is coming from all directions in the sky. And again, we have instruments which are located on exotic places on the surface of the Earth, for example, the South Pole. This is a South Pole telescope, and McGill has a major involvement in the South Pole telescope. And there are also microwave telescopes which orbit the Earth, which are in outer space. For example, the WMAP telescope. And with these telescopes, we look at the intensity of the microwave background in different directions in the sky. So again, a projection of the sky onto a plane, and this color coding indicates the different temperatures, the different intensities of microwave radiation. And you see, it is very isotropic. You have to explore at the level of 10 to the minus 4 of this temperature until you start seeing anisotropies popping up. Hot spots, cold spots. Now once you have this beautiful map, you can expand this map in spherical harmonics, and you can plot the power as a function of spherical harmonic or as a function of angular size. And this beautiful map leads you to the black points with some statistical uncertainties on small angular scales and some systematic uncertainty on large angular scales. So this is the data. So there is structure in the universe which has a very specific, interesting pattern, and we would like to explain this. And there's an artist who was given the freedom to draw a smooth curve with 6 free parameters that fits this data fairly well. And this artist drew this red curve. And I'm going to tell you who the artist was. And some of you, especially those of you who have heard a little bit about cosmology will be surprised when you hear the name of the artist who I mentioned. Okay, so you see that the second major goal of cosmology is to explain the origin of this beautiful structure, the patterns in the distribution of galaxies and anisotropies in the cosmic microwave background maps. And the third key point is we want to make predictions for future observations. That's a key aspect of what we want to do. We don't just want to explain things that we've already seen. We want to probe the way for future. We want to indicate to observers what are key things to focus on. And we are in a beautiful situation that we have lots of new windows to probe the universe opening up. For example, 21 centimeter radiation. So here is a new telescope with major McGill contributions, the CHIME telescope, which is probing 21 centimeter radiation, which is coming from the sky. So the groups of Professor Dobbs and Professor Caspi are playing a major role here. Then there's the HIRAX telescope, located in South Africa, with a major McGill contribution, Professor Sievers and Shan. Since Adrian is sitting here, there's HERA, again, a telescope in South Africa with major McGill contribution. And finally, there's a telescope which is located at the windiest point on the surface of the Earth, continental surface of the Earth, Marian Island. This is the PRISM telescope of, where Cynthia is PI for. So, I've only shown you one observation window. So we are going to have lots of new data, and we want to make predictions for what will be seen. So this is why I think cosmology is an exciting field. So the existence of the microwave background has told us that the universe has been expanding for a long time. So this illustration, time is the horizontal axis. An artist's illustration of the size of the universe is the vertical axis. We are here today looking at the universe, and the universe originally was very small, very hot, and there was a time when atoms combined, and that gives off the glow that we now see in the microwave background. Now, what is the framework that we use to describe the evolution of the universe? And the framework that was developed in the 1960s is standard Big Bang cosmology, which is based on three assumptions. Assumption number one is that space-time is described by classical general relativity. Assumption number two is that matter is described by classical gases. One gas is the gas of stuff that forms galaxies, pressureless gas, cold matter. And the other component is radiation, which we now see in the microwave background. Pressure equals 1/3 energy density. And finally, we assume, or in the 1960s it was just assumed, that the universe is homogeneous and isotropic. And that means that we can describe the nature of space-time in terms of this simple formula, which gives us the proper distance between events localized at different times and different points on the expanding surface. So x are the co-moving coordinates, which are coordinates painted onto the expanding sphere of the universe, and a of t is a measure of the size of the universe, the scale factor. And the change of a, the first derivative of a, that's the Hubble expansion rate. Now, standard Big Bang cosmology had a number of successes. It explained Hubble's law. In fact, Einstein could have predicted Hubble's law, except that he introduced this strange concept of a cosmological constant, and therefore he did not make the prediction. He had to make a postdiction. But standard Big Bang cosmology predicted the existence and black body nature of the cosmic microwave background. And also it predicted the abundances of life elements. So just a couple of slides on this. This is the redshift distance relationship of supernova, which shows you that the universe is, that space is expanding. And this timeline, which follows from standard Big Bang cosmology, predicts that the universe early on was a plasma, and the recombination of the plasma, which is illustrated here, gives rise to the emission of photons, and these photons are the microwave background. Now, the major success of standard Big Bang cosmology is illustrated in this graph. So this is the spectrum of the microwave background, let's say in one direction in the sky, intensity as a function of frequency. And this is the experimental curve, including error bars. So, for those of you who say cosmology is just order of magnitude, it's not really science, this is the best black body which had ever been accessible to humankind when this was made. So some of cosmology is now high precision science. So this is a spectacular success of standard Big Bang cosmology. But is standard Big Bang cosmology right? Should we rest on these successes? No, we shouldn't. So there are lots of things which standard Big Bang cosmology does not explain. It does not explain the large size and the large entropy of the universe. It does not explain the observed inhomogeneities. There is no explanation for all of this nice structure which I showed you before. And it is causally not possible to come up with an explanation in the context of standard Big Bang cosmology. Now that was nodding your head, but be careful here. I'm slipping in a slight lie. So for students here, you be careful here. I've slipped in a very slight lie when I said that it is causally impossible within standard Big Bang cosmology to explain the distribution of galaxies that we see. There's a very slight. So a mathematician would immediately notice the mistake. But anyway, we don't know how to do it. So don't worry too much. Don't look in textbooks, because textbooks say exactly what I said. But there is no explanation for the isotropy of the microwave background. And this I will illustrate briefly on the board. So if we have time, and we have space, and this is a time when the microwave background is released. We are here today looking at the microwave background. So this time interval is 13 billion years minus 100,000 years. This is 100,000 years from the Big Bang until this time. So light can travel this distance, but we've seen light coming from here to here, and therefore there's no causal contact between this point and this point, and therefore there's no way to tell this point to have the same temperature as this point. So this is this point here. Now, the second picture is why there's no explanation for the origin of structure in the universe. And so here the students have to be careful, because I'm now slipping in my line. Okay, so be careful. Good. So I'm drawing now co-moving coordinates, not physical size, but co-moving coordinates. These are the coordinates that are expanding as the universe expands. So, good. This is the time, again, it's the time of equal matter and radiation, which for the purposes of this colloquium you can view as a time of recombination. So, okay. So now we view the horizon. This is the maximum distance that light can travel from the Big Bang, starting at a fixed point. It's a maximal length scale of information transfer. And here I will plot wavelengths of inhomogeneities. So these are wavelengths. For example, this is the wavelength of the CMB quadrupole. This is the wavelength of galaxy clusters. And now, I'm not fooling you when I draw the curves this way, in the sense that this length scale is larger than the horizon at equal matter and radiation. It's not here where the mistake is, where the error is. But anyway, I'm now going to argue that we see structure today. It had to have been present at equal matter and radiation. And since this length scale is larger than the horizon, there's no way to produce structure on this scale. So therefore, in standard Big Bang cosmology, no explanation for the ordinary structure. And finally, there's a singularity at the beginning, which means that physics breaks down. So this is an incompleteness. So based on these problems, we realize that we have to modify the evolution of the universe, our cosmological model. And we modify the history of the universe at very early times. And very early means before the time of nucleosynthesis, before the time when the abundance of light elements was generated. Because we know that standard Big Bang cosmology is very successful after that time. So if we modify something, we want to modify it before. So that's now the link between early universe and structure. Okay, so now I'll come to these questions. Who is the artist who drew this red line? We want to explain this data. The acoustic oscillations in the angular power spectrum of the microwave background. So now, the people who first discussed this in detail were Zeldovich and Zinaev and Peebles and Yu in 1969, 1970, which is 10 years before the development of inflationary cosmology. 10 years before the development of inflationary cosmology. And here is a drawing. It's a poor reproduction from a paper by Zeldovich and Zinaev. Here is co-moving spatial coordinates, like the coordinates I drew here. This is time. This is the time when the microwave background is released. And this is the length scale below which inhomogeneities oscillate as a function of time, above which the fluctuations are frozen in as standing waves. So technically this is a Hubble radius, and that plays this key role. I'll come back to it. So Zeldovich and Zinaev and Peebles and Yu said, well, we see structure in the distribution of galaxies which looks roughly scale invariant. So let's assume that in the early universe, there was some way of setting up plane wave perturbations, plane wave inhomogeneities in matter with a spectrum which is approximately scale invariant. If this is the case, then these fluctuations start to oscillate when they cross this length scale. This scale does no oscillations. We catch it at maximal amplitude, peak in the microwave background. The scale that has done a quarter of an oscillation, we catch it at a minimum, maximal velocity, so at a minimum of anisotropies. So this picture here, different scales do a different number of oscillations between when they start to oscillate and when the microwave background is released, predicts this curve. So, this was all understood very well 10 years before the development of inflation. So this is what I said. It's prediction number one, which comes from Zeldovich and Ziniaev, Peebles and you. And this figure here, figure 1a, well, there's also figure 1b. Figure 1b shows you the matter power spectrum as a function of wave number. And the same oscillations that I discussed here give rise to oscillations in the matter inhomogeneities, the power spectrum of matter perturbations. These are called baryon acoustic oscillations. They were also discovered in about 2000. So it's all predicted 10 years before inflation. But the one question which was not answered in 1970 is, how does one obtain such a spectrum, a scale-invariant spectrum of fluctuations? And indeed, inflationary cosmology is a wonderful model. It is a first scenario based on causal physics, which yields such a spectrum, but it is not the only one. Okay, so now I will try to develop the criteria which a successful early a locally causal mechanism to generate fluctuations. So let's imagine the universe is a soup, the early universe is a soup. You want to create inhomogeneities by taking some label and stirring the soup. This is a local process that acts over a short time scale. So if you want that to happen, then fluctuations that we see today have to originate inside the Hubble radius. So the wavelength of fluctuations, which we see today, has to originate inside the Hubble radius. Otherwise, we cannot stir the soup to create perturbations. So that's the second criterion. And the third criterion is, well, we also have to generate an approximately scale-invariant spectrum. So these are the three criteria for successful early universe cosmology. And indeed, inflation satisfies all three. So here's a space-time sketch of inflation. So here was a space-time sketch of standard Big Bang cosmology. Here's a corresponding thing for inflation. Inflation is the idea that there was a period in the early universe, long before nucleosynthesis, when space expanded almost exponentially. Now, if space expands exponentially during this period, then the horizon expands exponentially. But the Hubble radius, which is the inverse expansion rate, is approximately constant. So inflation generates this exponentially larger horizon than the Hubble radius. Criterion 1 satisfied. Now, this red curve is the wavelength of a fluctuation mode. And the wavelength expands as the size of the universe, as the radius of the universe, proportional to the scale factor. So during this period of inflation, this red curve also expands exponentially. So as long as inflation lasts long enough, all scales that we observe today started out inside the Hubble radius at early times. And so we can imagine a locally causal mechanism which generates fluctuations. So criterion 2 is satisfied. Now, since the energy density is constant in this phase, in spite of the fact that the universe is expanding exponentially, so the universe is expanding exponentially, the energy density is constant. Very strange. But this is what is assumed in inflation. So if you have constant energy density, then whatever mechanism works to generate fluctuations, it will do the same thing at all times. You get a scale-invariant spectrum of fluctuations. Argument due to Bill Press, 1980. So inflation is successful, wonderful. But there's other ways to satisfy these three criteria. So one way is a bouncing cosmology, where you assume that the universe started in the contracting phase, which is a mirror inverse of standard Big Bang expansion. And then there was a short period of new physics which generates a transition between contraction and expansion. So this is what the scale factor does as a function of time. This is our standard Big Bang expansion. This is the mirror inverse contracting phase. And now you see that time runs from minus infinity to plus infinity, so the horizon is infinite. This is what scales of fluctuations do. They start out inside the Hubble radius. Criterion 2 satisfied. Now, I have to tell you, you have to accept the following statement. If the fluctuations originate by the same mechanism as they do in inflation, then the evolution of these fluctuations on super-Hubble scales leads you to a scale invariant spectrum of fluctuations. This, I don't have a heuristic explanation. I would have to refer you to equations, but I'm not cheating it. Now the third scenario is an emergent universe, where we assume that there's some early phase where there might not even have been a space, some new, maybe some condensed matter system, and then there's a phase transition from this emergent phase into the standard Big Bang phase of expansion. So I'll come back to that at the end of the talk. So this gives rise to this space-time diagram. Emergent phase, standard Big Bang phase of expansion. Emergent phase, static, Hubble radius infinite, which I sort of indicate here. This is a phase transition. And quasi-static means the wavelength of fluctuations constant. Okay, so time runs from minus infinity to plus infinity. Horizon is infinite. Criterion 1 satisfied. Fluctuations emerge sub-Hubble. Criterion 2 satisfied. What gives you scale invariance? Well, we need a little bit of help from our string theory friends, and I'll come back to that later. Okay, so this was a very lengthy introduction. Now comes inflation. So I already told you that inflation is the idea that there's a period of nearly exponential expansion during the early universe, during this period. Beginning of inflation, end of inflation. Before that time, there was regular cosmology, and therefore there was a singularity at some point before this time. Inflationary universe has a singularity. Now, if you want inflation to be successful, then unless you fine-tune parameters, the energy scale of inflation has to be 10 to the 16 GeV. To put this into context, this is 10 orders of magnitude higher than scales which are probed at the Earth, for example at LHC. And it's only about 2 orders of magnitude different than the Planck scale, where we know that we don't understand the physics. So just a warning here. We are now in inflation. We are working at energy scales which are many orders of magnitude removed from what we can probe. This is a timeline. This is a fancier illustration of this timeline. So compared to a non-inflationary universe, in an inflationary universe, you start much smaller to get fixed size today. This I will show you. Inflation is successful. Inflation creates a large, homogeneous, and spatially flat universe. Classical matter redshifts during inflation. You're left with a matter vacuum. And if you postulate, as Chibisov and Mukhanov did, and Stravinsky did, that quantum vacuum fluctuations are the seeds for the observed density fluctuations in gravitational waves, then you get what are now called the standard predictions of inflation. You get an approximately scale invariant spectrum of density fluctuations in gravitational waves, a small red tilt of density fluctuations, a small red tilt of gravitational waves. Red tilt means slightly more power on large wavelengths than small wavelengths. That's what red tilt means. focus on this. Because the model that I'll present at the end of the talk will give you a small blue tail, not a small red tail. Okay, so wonderful. Now how do we get inflation? So if we work in the context of general relativity, then we need matter with an equation of state pressure almost equal to minus energy density. Definitely pressure smaller than minus 1/3 energy density. This is a strange equation of state from the point of view of physics experiments. So what do you do? Now, high-energy physicists have a trick. If they want to do something which is hard to do, they invent a scalar field. Now, compared to other fields, scalar fields have a potential energy function. Now, you can design your potential energy function to do anything you want. You give me a scale factor of the evolution of the universe, I can construct a scalar field potential which gives you that. Okay, good. So now, so the key point is that the potential energy acts a little bit like a cosmological constant, which is something that gives you this equation of state. But other contributions to the energy don't have this equation of state. So if you want inflation, you have to make sure that the potential energy dominates over the other forms of energy. And then you need a slowly rolling scalar field. So this is a requirement on the slope of the potential. V prime is derivative with respect to the field. And the field has to roll over large distances. Okay. So you need this. So you need to invent a scalar field, invent a potential function, which is rather flat. Okay. So, good. Now, you would like not to have to fine-tune your initial conditions. Because if you need to fine-tune initial conditions to get inflation, you've replaced one fine-tuning condition by another one. And now I just want to mention, because there's a lot of contradictory statements in the literature about initial conditions for inflation. Now, if you have large field inflation, where the field rolls over a distance larger than m Planck, you can show that the inflationary solution is a local attractor in initial condition space, in the sense of dynamical systems. Small field inflation, it is not. You have to fine-tune initial conditions. So therefore, if you want inflation to be free of initial condition problems, you want large field inflation. Even for large field inflation, there's a small caveat, but that's a small caveat in opportunity. Okay, so everything I've said until now is not controversial. Now will come the things where I will be more controversial. So, instead, we didn't rest on the successes of standard Big Bang cosmology. We were focusing on the problems, and then we were able to make progress. And my philosophy is to try to do the same with inflation. So what are the conceptual problems of inflation? Well, there's a singularity. Inflation is not complete. How do we obtain inflation? Well, inflation takes place at energy scales close to the scales where we need to focus on quantum gravity. So let's be a little bit more specific to that. Let's take this diagram, which you've seen several times. Physical size versus time. This is the wavelength of stuff that we observe. And if inflation lasts long enough, then the wavelength starts out sub-Hubble, which is what we want. But if inflation lasts just a little bit longer than we need it to, then the wavelength starts smaller than the Planck length. And we know that our theories break down. This is a load of ignorance. So this is dangerous. And based on this danger, 2 years ago, Waffer and Brandenberger postulated the trans-Planckian censorship conjecture. And their statement is that no cosmology consistent with quantum gravity can have the properties that trans-Planckian modes with an initial wavelength smaller than the Planck length become larger than the Hubble radius, larger than the scale where fluctuations classicalized become measurable. So, mathematically, this means the following. We take the initial Planck length at this initial time. The length expands, and at a later time, we want the physical wavelength to be smaller than the Hubble radius. This is the condition. Okay, now one analogy is black holes. So this is a diagram of a black hole with charge smaller than the mass. So the center of the black hole, distance from the black hole, this is sort of the observer time of an observer at infinity. Now you have an observer outside of a black hole. If there's a horizon, if the charge is smaller than the mass, then the observer cannot see anything that comes from the inside and nothing that comes from the singularity. This is a singularity. We know that physics breaks down here, but the observer is safe. Now if we take a black hole which has charge greater than mass, and in general relativity you can construct such solutions, then the poor observer can access the singularity. And all kinds of mathematical and physical problems result. So Penrose postulated that in spite of the fact that general relativity allows for solutions with these time-like singularities, which are disastrous for observers, that the correct ultraviolet physics, the things that will compete general relativity, will prohibit these solutions, these pathological solutions, to appear. So this is Penrose's cosmic censorship conjecture, a very famous conjecture. Now what I will do is I will translate this to cosmology. So position space, momentum space, singularity, trans-Planckian modes, black hole horizon, Hubble horizon. And Penrose transformed from black hole physics to cosmology, says the observer outside of the Hubble radius must be shielded from the trans-Planckian modes. Cosmic censorship, the trans-Planckian censorship conjecture. In light of time, I will skip this and I will skip this. Oops. Now, let's apply this to inflation. So, this is my space-time diagram for inflation, the inflationary phase, after inflation. Now, inflation cannot last longer than I drew here, because the way I do it here is that the initial wavelength, the initial Planck length, becomes exactly the Hubble radius at the end of inflation. So this is an upper bound on the duration of inflation. But if we want scales that we observe today to emerge from inside the Hubble radius, we get a lower bound on the duration of inflation. And a little bit of mathematics shows that these conditions are compatible only if the energy scale of inflation is 7 orders of magnitude lower than what we would actually like for inflation. And that implies that if you have an inflationary model that satisfies this, you get no visible primordial gravitational waves. Okay. This also has implications for dark energy. It means that dark energy cannot be a cosmological constant. Dark energy has to be more interesting than a cosmological constant. Now the second problem, the second constraint on inflation comes from string theory. So, now many people are negative about string theory these days because they say that string theory can give you anything you want. You have all these possible solutions of string theory. Well, let's deconstruct this argument. So, if you stick to effective field theories, point particle field theories, you have a huge landscape of possible theories. Any space-time dimension goes, any number of field goes, any shape of the potential goes, any field range goes. If you demand that this theory comes from string theory, it is extremely constraining. You have a fixed number of dimensions. It happens to be 10. We can come back to that a little bit later. Each scalar field has a geometrical origin, and the physics determines the potential. Very constrained. So most effective field theories are not consistent with string theory. So as illustrated here, you have this ultraviolet complete theory, this huge landscape of effective field theories. Most of them are inconsistent with string theory. Now what are the criteria for theories consistent with string theory? Well, the potential has to be steep, or else the potential has to be sufficiently tachyonic. This obviously means simple canonical inflation is out. Small problem, because inflation requires the potential to be shallow. Okay. Good. Right. What about alternatives to inflation? Balancing cosmologies are consistent with the transplanted censorship conjecture as long as the energy scale of the bounce is smaller than the Planck length. Same thing here for emergent cosmologies. So it is precisely inflationary cosmology which has these problems, and precisely because of the exponential expansion says. But again, be aware that these are controversial statements that I'm making. So I'm coming now close to the end, so let me say a little bit about new ideas. So if we start with string theory, what kind of cosmology will we actually get? So from now on, I will start with string theory. Okay, so an old approach is the following. Let's do the same with string theory as we do with particles when we develop standard Big Bang cosmology. We have space, we have a gas of particles. In string theory, you have space, a gas of strings. Okay. So what we want to do is we want to use the differences between strings and particles. We want to use the new degrees of freedom that strings have, which point particles don't have, the new symmetries. And strings are not just points. So strings can wind space. Point particles cannot wind space. And strings have oscillatory modes, like guitar strings. And the fact that strings have oscillatory modes leads to the fact that a gas of strings has a maximum temperature. And the fact that you have winding modes leads to the fact that a small box of strings behaves exactly the same as a large gas of strings, as a large box of strings, where large and small is relative to the string scale. This is this TUR symmetry. So, energy of point particle modes in a box of radius r, energy of winding strings in a box of radius r. So you see that if you replace if you interchange n and m, and you let r go to 1 over r, it's a perfect symmetry. It's a symmetry of interactions of strings. It's a symmetry of non-perturbative string theory. And so therefore it's a good symmetry to explore. So now if you take your box of strings with radius r, and you look at the temperature, you compress the box, the temperature will initially rise, but then it will level off. It will level off because here you have so much energy density that it will start to create the oscillatory modes. When you cross the string scale, the temperature will go down because all the energy is dumped into the winding modes. So this is very different from the point particle picture. RT, singularity, no singularity. So there's a very good chance that if you really manage to develop a good string cosmology, it will be non-singular. Okay, so now we are going to assume that there's a dynamics. That says that the universe starts out here, or we start the evolution of our universe when we are in this phase. This phase will last a long time, and eventually you have a transition where the winding modes are decaying into loops, and that's what generates the radiation that we see today. And this is the thing that generates this evolution of a scale factor. constant in this early phase, and then standard Big Bang cosmology. So this is argued to emerge from string cosmology. It is argued to emerge without equations. Good. So this picture emerges. And so therefore we can now ask the question, what are the density perturbations in gravitational waves which are produced? Okay? So here we don't have a vacuum. We have a thermal gas of strings, so we have thermal fluctuations, not vacuum fluctuations. And we have thermal fluctuations of strings, not of point particles. So we put this all together. Here are the equations. We compute energy density fluctuations in a thermal gas of strings, off-diagonal pressure perturbations in a gas of strings. We managed to compute the density perturbations, the curvature perturbations, and the gravitational waves. I realize that I'm just sketching what we are doing here. Upshot is that we can compute the spectrum of curvature perturbations, and it is scale invariant. We compute the amplitude. We find that we get the same results for the spectrum of curvature perturbations as we do for inflation. It is scale invariant, small red tilt. We look at the gravitational waves. Scale invariant, small blue tail, unlike inflation. And this is the prediction that we are making that comes from string cosmology. Now, do I have another couple of minutes, Bill?
Sure, yeah.
Okay, where do we stand? So it looks like string gas cosmology is a promising alternative, but how do we really describe the emergent phase? Not in terms of words, but in terms of equations. This is what I view as the Achilles heel of our current understanding. So now this is the transition from the point where I understand what I was talking about to where I no longer completely understand what I'm talking about. Okay, so be aware, it's a second transition. So there are various ideas that we've been exploring. One of them is double field theory, and this is something I'm working on with Hayes and Bernard, with Paul, and former student Guillermo Franzmann, who's now a postdoc at Modita. And this is based on this T-duality symmetry. So now, in quantum mechanics, it is known that the position operator is dual to the momentum operator. I think all of you who've taken quantum mechanics will know. Now, in string theory, you have something that's T-dual to momentum, namely the windings. So therefore, you have a dual position operator, dual to the winding. X and X tilde. They're equally good position operators. For small boxes, these are light modes, and an experimentalist would have a stick made up of these operators. But at small boxes, this measuring stick will disintegrate, and a new measuring stick will arise, made up of the winding modes. Okay, so what we argue is, so this is what I just said. So now in the early universe, we expect the size of the universe to be string scale, and at the string scale, both X and X tilde are important. You cannot neglect one versus the other. And as a consequence, the usual effective field theory based on supergravity will inevitably break down. And double field theory is an attempt to develop an effective field theory which lives in this double space. In particular, it will live in 18 space dimensions. Okay, so this is one approach. Now, double field theory is not full string theory. It does not contain the oscillatory modes. So let's look at another approach. Now, this approach is even more off scale and maybe completely wrong. But this goes back to an idea which was put forward about 20 years ago by Banks, Fisher, Schenker, and Susskind. And there's parallel work by a Japanese group, IKKT. And it was an attempt to define non-perturbative string theory. So it's non-perturbative approach to superstring theory. And the idea is that you start with a quantum mechanical matrix model. So matrix model, quantum mechanics, no fields, just matrices. So it's obviously no singularities. But there's also no space. So now these matrices, you take 10 matrices and you go the n going to infinity limit. So these are n by n Hermitian matrices. Okay, so what happens? This is the form of the Lagrangian. These are 9 xi matrices, and there's another matrix hidden in this gauge covariant derivative. That's the matrix that corresponds to the time matrix. So now the group in Japan has been able to show that if you take the eigenvalues of A0, that they become emergent time, which is continuous in the n going to infinity limit. Since these are Hermitian matrices, you can always diagonalize one of them. We diagonalize A0. Now it turns out that if we work in the basis in which A0 is diagonal, these xi matrices become block diagonal, and that gives you emergent space, which again becomes continuous in the n going to infinity limit. And you can explore the growth of space as a function of time. So this matrix model gives you emergent time, emergent space. Local Lorentz invariance emerges simply because there is an eta ij symbol in here. So, and now it turns out that if we compute if we assume that this matrix model starts out at high temperature in a thermal state, then we can compute thermal correlation functions. And what we found is that we get the same thermal correlation functions as we got in string gas cosmology. Okay, so basically we are claiming now that the BFSS matrix model, which is this non-perturbative proposal for superstring theory, yields emergent space, emergent time, and an emergent universe phase with clear predictions for observations, namely this blue tilt of the gravitational wave spectrum. But this is probably wrong. But maybe it will point to an avenue for improvement, and so I've probably exhausted Bill's patience, so I'll go to the conclusion. So, first of all, we have lots of data about the cosmos, and much more data is expected soon. Now, cosmological data can only be explained using new fundamental physics. You have to modify the early universe if you have a chance to explain all the data. Now the current paradigm is cosmological inflation. And this has been very successful. It opened the door to probe, to try to understand what we see today using fundamental physics. So it played a very important role. And when it was first developed, we had hardly any data. It made lots of predictions, lots of successful predictions. But it suffers from conceptual problems. Standard inflation, the way I presented it, based on perturbative quantum field theory. Okay. Alternatives to cosmological inflation exist. So these are conclusions I want you to walk away with. These I call non-controversial. And then, well, this is sort of the dessert of this talk. So thanks.
Thank you very much for this very nice start to the academic year. We can take a few minutes of questions. We're just up at the edge of time, so just a few. Please at the back.
You said in string gas theory the universe is compact. I'd like to know how big it is.
Yes, it is at least 10 times as big as the presently observed size of the universe.
Peter?
Thanks for a great talk. What does slight blue mean? Like, is this measurable, or is this like 1 part in 10 to the whatever, What-
Okay, so we have a concrete, in string gas cosmology, we have a concrete formula.
Like a number.
Namely, the blueness is equal in magnitude to the redness of the cosmological perturbations. And so that number we know from observations, so therefore we give a specific prediction.
And is it measurable?
Not now, but we see observation cosmology has made tremendous progress. So, okay, so now I'll give you the number. So the NT is predicted to be about 0.04. What we could measure now is 0.2. And this is a number about 5 years ago. Maybe it's tight now.
Sure.
So you see by how much,
Yeah, please.
So I think I understood your explanation for how emergent cosmology could explain isotropy and structure, but I missed, does the spatial flatness of the universe also arise out of
Very good question. You didn't miss it, but I didn't tell you because I don't know. There are some vague ideas, but the honest answer is that I know about this question. I'm fully aware of it, but I don't have a good answer.
Please.
Do you have reasons to believe that the universe might not be homogeneous and isotropic
Well, it is not homogeneous and isotropic on small scale.
on large scale?
Now okay, so you see, I'm going to pass on this question because we see convergence to homogeneity if we probe larger and larger, and there's certain evidence that you might have some deviations. You're referring to Chubia-Sarkar's work,
Yes.
and there, I think we have to keep an open mind, but I don't see any conclusive evidence. But I'm not the right person to comment on it.
I think I saw a question over there. Please go ahead.
Question. So you said that inflation has primarily conceptual problems, which is mainly that we don't know what happens beyond the zone of ignorance, right? Like the Planck scale situation.
That is one set of problems. The other set of problems is that we don't know where this scalar field comes from, which has a sufficiently flat potential.
But then,
Potentials that I know how to construct all have a steeper potential. All are steeper.
but then there is no real cosmological data that contradicts inflation.
No, that's right. Inflation is consistent with the data that we have. See, if we look at the things that standard Big Bang cosmology explained, there was no contradiction. The microwave background is the black body. You have to look at the things which were not addressed. And that's a way to make progress, in my opinion.
And I think Paul is going to ask the last question.
Yeah, it's a very stupid question. I would say more data are coming soon, so when do we know about this blue versus red? It's like, I want to know, Robert. Tell me.
You see, I'm a pencil and paper theorist. I'm all about it. So you have to ask Adrian or Matt Dobbs.
So,
Well, I mean, that's a CMB polarization question, so I'm going to throw it to Matt.
Okay, unfortunately, we don't have a wine and cheese, so you'll have to continue the discussion on Slack or your favorite other online channel. But let's thank Professor Brandenberger once again. Next week we'll have another guest from Concordia University. It'll be Ray Mansbach. Please come back.